All right, welcome to this explainer. I am so thrilled to have you here today because we're looking at what is honestly one of the most incredible engineering feats of our entire lifetime: autonomous vehicles. We hear about them all the time, right? But we rarely stop to actually think about the monumental, mind-bending technical challenge happening right under the hood. So today, we're going completely behind the scenes to decode exactly how a self-driving car actually perceives the world around it. It's absolutely fascinating stuff, so get comfortable and let's jump right in.
Okay, let's dive into this. As a human driver, you do something staggeringly complex without even batting an eye. You can just glance at a completely chaotic, busy street and instantly understand it. You immediately know, okay, that's a car, that's a kid on a bike, and that's a red light. And actually, more importantly, you know that a puddle on the ground is just a puddle, but a dark patch right next to it, that might be a pedestrian's shadow. A self-driving car has absolutely none of that intuition built in. When it looks at a street, it is literally completely blind in the human sense. And really, that brings us to a huge core problem: human intuition versus raw electrical signals. We intuitively just grasp context, but a self-driving car, it starts with a total blank slate. All it gets is this flood of raw electrical signals from a bunch of hardware sensors. From those totally abstract signals, it has to build a complete, perfectly accurate three-dimensional model of the world around it. And it doesn't just do this once. It has to rebuild that reality dozens of times every single second. It's got to do it in pouring rain, in the dead of night, and with the glaring sun right in its eyes. This monumental task of turning raw sensor data into actual understanding, that's what engineers call perception.
Section 1, a car's digital senses. Let's look at exactly what hardware makes all of this possible. So to pull off this absolute miracle of perception, the car relies on a stack of different digital senses. First up, we've got cameras. These are essentially the eyes of the car, and they're definitely the closest thing to our own human vision. They are incredibly rich in information and, relatively cheap to install. Cameras are what allow the car to actually capture color, read road signs, see lane markings, and tell the difference between a green and a red traffic light, which is great and perfectly illustrates their immense value. But it also highlights their fatal flaw. A camera produces a flat, two-dimensional image. Because of that 2D flattening, judging exact distances is incredibly difficult for them. And just like our human eyes, they struggle heavily with sun glare, low light, heavy fog, and pouring rain. Well, that brings us to our next sense: radar. Radar works by firing out radio waves and then just listening for the echo to bounce back. Now, to be clear, it is not detailed at all. Radar cannot read a stop sign, and it definitely can't tell the difference between a person and a light pole. But here's the crucial point. It is brilliant at two specific things that cameras are terrible at. It can perfectly measure how far away an object is and exactly how fast it's moving. And best of all, it can do this reliably in dense fog, heavy rain, or total darkness. Radar is basically the rugged, heavy-duty backup sense that keeps working when the weather turns ugly. Moving beyond basic radio waves, we find a truly incredible piece of tech: Lidar. That stands for light detection and ranging. Think of this as a robotic sixth sense. It's actually the signature sensor you see on most modern robotaxis. Lidar physically spins around, firing hundreds of thousands of invisible laser pulses every single second, measuring exactly how long each one takes to bounce back. The result is what engineers call a point cloud. It's this wildly precise 3D model of everything around the car that is accurate down to the centimeter. It gives the car perfect shape and distance awareness. But much like cameras, heavy rain or snow can really degrade those laser pulses.
Lidar's biggest historical weakness, however, wasn't the weather. It was this number right here: $75,000. Back around 2015 or so, that was the staggering cost for just a single Lidar unit. I mean, it was a massive financial barrier that made outfitting an entire commercial fleet almost impossible. But wow, look at how far the engineering has come since then. Today, the cost of a Lidar unit has plummeted to roughly $500. That is just an unbelievable drop. Although it is definitely worth noting that if you're a car manufacturer trying to build millions of vehicles, adding an extra $500 per sensor still represents a highly significant cost at that kind of mass scale. To finish building our car, we need to round out the hardware with a few final pieces to complete the sensor stack. We've got ultrasonic sensors. These basically act as close-range feelers for low-speed maneuvers. They detect curbs and objects just inches away while you're parking. Then we have GPS and inertial sensors to track the car's rough location and physical orientation.
And finally, some companies, like Waymo, use HD maps. These are pre-built, centimeter-accurate memories of every single street they operate on. This means before the car even arrives at an intersection, it already knows exactly where the lanes, curbs, and traffic signals are located. So it only has to worry about tracking what has actually changed, like other cars and pedestrians. Section 2, Sensor Fusion. Let's see how this all builds into the ultimate engineering solution. Because here is the real secret to autonomous driving. No single sensor is trusted on its own, ever. The real magic happens in a software step called sensor fusion. This is the process of combining all of those totally different hardware inputs into one single, unified reality. The car's software literally takes the precise distance points from the Lidar, matches them up with the colored pixels from the camera, and then stitches the whole thing together with the speed readings from the radar. A single object on the road is confirmed by several senses all at once. So if the camera is blinded by a sunset, the radar and Lidar still confidently report that solid object ahead. Each sense perfectly covers for the other's blind spots. It's brilliant. But having a perfectly fused cloud of points just isn't enough on its own. The car has to actually understand what it's seeing. This is handled by neural networks, AI trained on enormous amounts of driving data, executing this relentless three-step loop. Step 1, detect and classify. The car has to instantly label every object. Okay, that's a cyclist, that's a fire hydrant, that's a traffic cone. Step 2, track. It has to follow each object frame by frame, making absolutely sure it knows the pedestrian it saw a millisecond ago is the exact same pedestrian moving right now. And step 3, predict. This is the absolute hardest part. The car has to estimate what each object is going to do next. Is that car about to merge? Is that pedestrian about to step off the curb? It has to anticipate, not just react, before it ever decides to turn the steering wheel or hit the brakes. Section 3, the great sensor debate. Now, what's really fascinating here is the massive, unresolved schism currently dividing the entire industry. We are looking at a genuine, ongoing philosophical debate about which senses a self-driving car actually needs to be safe. We essentially have two major camps. On one side, you have the vision-only approach, championed famously by Tesla. And on the exact opposite side, you have the sensor fusion approach, utilizing multiple different sensor types, championed by Waymo and most robotaxi companies. Our goal here today is completely neutral, all right? We just want to unpack the fascinating engineering arguments driving both sides of this. So let's start with the vision-only camp. Their core argument is actually profoundly simple. The entire global road system is designed for eyes. Humans drive using only vision, so a machine should be able to manage with just cameras and powerful AI, right? Their method relies entirely on those cheap cameras backed by neural networks trained on literally billions of miles of real-world driving data. No Lidar, no radar. The massive pro here is scalability and cost. Because cameras are so incredibly cheap, you can ship this system on millions of consumer cars rapidly. The primary criticism, however, is that relying only on cameras means inheriting human-like weaknesses. If the cameras struggle with depth perception, total darkness, or severe sun glare, well, there is no independent weatherproof sense like radar to fall back on. In stark contrast, we have the sensor fusion camp. Consider this absolutely staggering breakdown of Waymo's current generation sensor suite on just a single vehicle. 29 cameras, 6 radars, 5 lidars. That is literally 40 total sensors on one car. Their argument is that safety can only come from absolute redundancy, having multiple, independent physical senses that catch each other's mistakes. If the cameras are blinded, the lidar takes over. If the lidar is blocked by a heavy snowstorm, the radar pushes right through. It creates an incredibly robust safety net. So if we boil this massive industry debate down to one single line, we have the core tension, cost versus redundancy. Fewer sensors are immensely cheaper and way easier to scale to millions of vehicles. But more sensors are inherently safer through physical hardware backup. The reason this debate rages on today is simply because nobody fully agrees yet on what the threshold for safe enough truly is when it comes to autonomous machines. Section 4, the long tail. Why is perfecting this technology still so incredibly difficult? The reality is, the everyday 95% of driving is largely solved by these companies. Cruising down a clear street in perfect weather, that's the easy part. The absolute nightmare for engineers is the final 5%, known in the industry as the long tail. These are the totally unpredictable edge cases. Just imagine a self-driving car suddenly encountering a couch abandoned right in the middle of the highway at 65 miles an hour. Or a human police officer using hand signals to wave traffic through a broken red light. Or, honestly, even just a large plastic garbage bag blowing across the road, which to a bouncing laser or radar wave might look exactly like a solid dangerous object. A car's perception system has to flawlessly handle these chaotic situations without ever having seen them before. And as we all know, the real world produces an infinite supply of this kind of weirdness. When you step back and look at everything we've covered today, you really realize a fundamental truth. A self-driving car doesn't actually see the road the way you and I do. It relentlessly builds the road from scratch. It mathematically assembles laser points, radar echoes, and camera pixels into a 3D model of reality dozens of times a second. And then, based entirely on that model, it has to guess what everything in that reality is about to do. Ultimately, every single engineering breakthrough we talked about, every intense sensor debate, and the entire future of autonomous driving really just comes down to this one profound question. How good can a machine get at that guess? It's a question that is absolutely redefining the limits of artificial intelligence. And I really hope this breakdown gave you a whole new appreciation for the incredible science happening right now on our streets. Keep asking questions, keep learning, and I'll catch you on the next explainer.